So our next speaker indeed is Challenger Mishra, who is a research fellow at Cambridge, and he will talk about machine learning Calabi-Yau metrics.
Can everyone hear me?
Yes, we can hear you.
Thanks. Thank you for the kind invitation to speak at this lovely gathering. I'm thrilled to be here. So I'll be talking about machine learning Calabi-Yau metrics. Before I begin, I wanted to highlight a new research group that I'm part of at the Computer Lab in Cambridge. We are called the Auxillary Program for Scientific Discovery. And essentially, we are a bunch of interdisciplinary researchers with different domain expertises, but all tied together by the use of machine learning in our respective fields. You can follow our activities at our website. Nonetheless, the paper I wanted to talk about today is titled Neural Network Approximations for Calabi-Yau Metrics. This is work done with Vishnu Jajjala and Damian Mayorga-Pena. Now, there has been a lot of interest in computing numerical Calabi-Yau metrics, and a lot of work has gone into in this direction over the last couple of decades or so. And there have been recent developments in building analytic Calabi-Yau metrics as well, coming from the work due to Shamit Khachru and others. Now, I wanted to highlight that there is now an increasing effort in employing machine learning to construct approximations for Ricci flat metrics over Calabi-Yaus, which is an essential ingredient in connecting string theory to four-dimensional physics. And all these papers that I have listed here, they are fairly recent, and they all highlight the promise of machine learning in this direction. Taking a step back and to motivate why we are interested in Calabi-Yau metrics in the first place, I wanted to mention that invariance of natural laws under symmetries of nature is a guiding principle for physicists. Newtonian mechanics is essentially something that comes from Galilean invariance. Electromagnetism and relativistic mechanics comes from Poincare invariance. General relativity comes from invariance under diffeomorphisms of space-time. And the standard model of particle physics, which is an important component in string theory, is invariant under certain gauge symmetries. And the standard model of particle physics is a theory that unifies electromagnetism, the weak and the strong nuclear forces. Now, the gauge group for the standard model of particle physics is SU3 cross SU2 cross U1. And typically, a string theory reduces to the standard model of particle physics via a grand unified theory. And although there are different candidates for gauge groups for grand unified theories, not a specific one, people haven't been able to specify one definitely. And at the level of perturbative string theory, you have invariance under certain gauge symmetries, depending on which version of string theory you might be interested in. Now, string theory is the only known consistent theory of quantum gravity. It is at this point that I expect tomatoes to be thrown at my face by loop quantum gravity people, but this is the advantage of a virtual conference, so I can dodge these. But the two main postulates or building blocks of string theory are the extra dimensions. String theory postulates extra dimensions of space, and it relies on a fundamental symmetry between matter particles and force carriers called supersymmetry. String theory is also an organizing principle for mathematics, and we see this play out in various different domains of mathematics, mirror symmetry being a prime example of this phenomena. Now, there are various different versions of string theory, and they are depicted as islands in this beautiful landscape. And there's a tiny boat of physicists who are trying to make sense of all of this. Also in the picture, superstring theory supplies a mathematical framework for obtaining the real world from a consistent theory of quantum gravity. And there are various ingredients that are at play here. The holy grail is to embed the standard model of particle physics within the framework of string theory. Here in the picture, I'm demonstrating different generations of fermions and gauge bosons and the Higgs boson that have all been experimentally seen at particle accelerators, and they form part of the standard model. So the goal of a string phenomenologist is to reproduce the particle content, coupling constants, masses of the particles, and so on. One should also be able to explain the origin of discrete symmetries in the standard model that often help explain unobserved couplings, the long lifetime of the proton, etc. There are various other challenges. One has to explain fine-tuning, supersymmetry breaking, and no such model till date has been found, but there has been considerable progress in building semi-realistic models over the last decade or so. Now, string theory unifies gravity and quantum mechanics and reduces to the standard model in the low energy limit via an intermediate grand unified theory, as I mentioned just a couple of slides ago. Now, this is called string compactification, where the low energy theory standard model is recovered by hiding away or compactifying over the extra dimensions of space. And this places severe geometrical constraints on the extra dimensions of string theory. And for the purposes of this talk, I'll focus on Calabi-Yau manifolds as candidate extra dimensions. Now, compactifications of the heterotic string is one of the more promising avenues for string model building. The space-time for the effective field theory is a direct product of a maximally symmetric space, which is 4-dimensional, and an internal compactification space, which is 3 complex dimensional. Now, which we denote by X6. If X6 is Riemannian, which is something that we need since we want to describe gravity. If it is irreducible, which comes from one's ability to explain or accommodate chiral fermions in the theory. And if we demand n equals to 1 supersymmetry in the 4D theory, then the holonomy of the extra dimensional part is fixed to be SU3. And these manifolds do indeed exist. And Calabi conjecture proved by Yau says that an n-dimensional complex scalar manifold with vanishing first-gen class does indeed admit a metric with SU1 holonomy. And this leads us to the class of Calabi-Yau manifolds. So from here on, we take the extra-dimensional part to be a Calabi-Yau threefold. Now, in the Andre, just in the previous talk, highlighted some features of some mathematical constructions that allow you to construct string models, and I would not reinvent the wheel by describing the same too much, but I will touch upon them. So in the simplest setting known as the standard embedding, the number of generations of particles that you retrieve from a string model is given by the Euler characteristic of the extra-dimensional Calabi-Yau space. And more generally, bundle-valued cohomology groups give you the particle spectrum of a stringy standard model. Now, heterotic string models can be obtained by considering a compactification over a Calabi-Yau X that admits a vector bundle phi. Now, if we have to go through this process of string theory breaking into a grand unified theory, which then breaks into the standard model, this is highly restrictive. And variations of the 10-dimensional heterotic effective action leads to these constraints, including constraints on the bundle. And these constraints are topological in nature, and satisfying these conditions lead to an anomaly-free theory involving stable bundles over Calabi-Yau threefolds. Now, in order to obtain a gut group that is as close to the standard model gauge group as possible, one must choose the structure group of the vector bundle V that is at play here as something that is larger than SU3, SU3 being the structure group of the tangent bundle of the Calabi-Yau X. Now, given a generically, or speaking more generally, given a vector bundle V with some structure group G, the grand unified theory group that this leads to is the commutant of G in E8. The gut group should contain the standard model gauge group and admit complex representations as well. So here's a couple of examples of how this symmetry breaking happens. Now, prior to 2008, only a handful of string-derived standard models existed. Now, owing to this beautiful construction of line bundle sums that appeared soon after, due to Laura Anderson, James Gray, Andre Lucas, Yang-Hui He, and later on Andre Constantine and others, there have been tens of thousands of semi-realistic standard models when one considers V to be a sum of line bundles. And in this construction, V is completely specified by H11 times the rank number of integers. H11 of X is a Hodge number of the Calabi-Yau geometry, and depending on, and you can fix the rank of the bundle as you wish. Now, without going into further details and getting distracted from the main point of the talk, I'll just describe a simple vanilla string model defined over this complete intersection Calabi-Yau, which I'll define soon. So here, the geometry X is described by the vanishing locus of these 4 polynomials defined over these 5 projective spaces. The diagram on the right is a bipartite graph representation of this matrix that describes the geometry. Another component of this construction is a discrete symmetry that is freely acting on the base geometry, and by an exhaustive scan that we did alongside Andre Constantine and Andre Lucas, we did an exhaustive search with some clever heuristics to classify all these vector bundles over certain CCs, leading to the gauge group, the gut group SO10 or spin 10. And this led to many tens of thousands of examples. This, of course, follows the construction of SU5 guts over the same class of geometries. Nonetheless, this also produced several tens of thousands of string models, and it's important to note that none of these models give a complete picture, but simply lead to semi-realistic string models that agree with the standard model in broad terms, for example, in terms of number of generations of particles and so on. Alongside, along with Andre Constantine, Andre Lucas, we did a statistical study of these string models and tried to understand what is the distribution of the number of generations of fermions predicted by these models, and we found this nature of plot which seems to be universal among the classes of geometries that we studied. Now, why study Calabi-Yau metrics? Thus far, we have been talking about topology, and topology on its own is sufficiently powerful to enable model building. But to go beyond an analysis of the particle spectrum, we must obtain the Kähler potential that leads to a metric on the Calabi-Yau. Now, knowledge of this metric will ultimately lead to computation of physical quantities such as masses of particles. And so therefore, the ability to actually make testable predictions or do consistency checks on heterotic string theory in this manner would require an understanding of geometry as well as topology of Calabi-Yau spaces. Now, there are many possible Calabi-Yau geometries, and this is the shield plot that is very famous within the community. And there are different classes of geometries that feature. Here, I'm showing a plot of the height of Calabi-Yau manifolds, which is given by the sum of its 2 Hodge numbers versus the Euler characteristic. And this is a list of around 500 million geometries. And these are all Calabi-Yau manifolds characterized by Kreutzer-Skarke. Now, the class of manifolds on which we would like to understand metrics are complete intersection Calabi-Yau manifolds, which have been mentioned earlier. So here, the general form of such a geometry is given by this configuration matrix on the left, where Q's denote the charges or the degrees of the polynomials that appear in this construction. The complete intersection Calabi-Yau geometry is essentially given by the vanishing locus of a set of n homogeneous polynomials with variables in the corresponding complex projective spaces. And vanishing first-gen class imposes a rather trivial condition on these charges, and it says that the charges in a row in this matrix should sum up to the number of coordinates in the projective space. An example of this is the simplest example of this is the Quintic geometry, which is denoted as just the matrix 5. It's defined as the zero locus of a degree 5 homogeneous polynomial with coordinates in CP4. And as all of you would have noticed, that without specifying these coefficients in the polynomials, we are actually talking about classes of geometries as opposed to singular examples in such classes. If one specifies the coefficients, then you are very local in the complex structure moduli space. Here are a couple of other examples. The first one is the tetraquadric, which has this beautiful bipartite graph, and the second one is a bigger configuration matrix, denoting a different Calabi-Yau with different topological properties. There are different transitions between Calabi-Yaus, and in the class of CICYs, there are these beautiful Conifold transitions that one can visualize using these bipartite graphs. They change the topology of the geometry in an incremental way. So all these bipartite graphs refer to different classes of Calabi-Yau, complete intersection Calabi-Yau geometries. Now, I'll make some general remarks about the metric. So as a complex scalar manifold of this Calabi-Yau, which we denote by M, the metric is a Hermitian matrix that can be derived from a potential. So the metric can be determined from the derivative of a potential. And it can be used to construct the scalar form, and the Ricci tensor corresponding to this metric is given by this terse expression defined in terms of the determinant of the metric. Now, a Calabi-Yau admits a metric with vanishing Ricci curvature. This is known, and it's also known that this metric is unique in each scalar class. But till date, no analytic expression has been found for a Ricci flat metric of a Calabi-Yau threefold. Therefore, one must settle for some approximations. So some of the manifolds we study in our paper, they are the Fermat Quintic, some members of the Dwark family. We also look at some K3 surfaces, and as well as the Tian-Yau manifold. The treatment on the Tian-Yau manifold is not as satisfying as on the Fermat Quintic or on the Dwark family, mainly because of a couple of issues. One being that it is a priori not clear which scalar class you are actually working with to begin with. However, the manifold is very interesting because a freely acting Z3 quotient of this geometry yields a Calabi-Yau yields a quotient Calabi-Yau with Euler characteristic -6, which is twice the number of generations of particles that you would expect. So therefore, this provides a geometry on which serious model building can happen. Now the transpose of the Tian-Yau is the Schoen manifold, and it can be represented in various ways using splittings and contractions using Conifold transitions. Now the methodologies, there are various methodologies for obtaining Calabi-Yau metrics or their approximations. Donaldson's algorithm has been around for a long time, and the approach in this paper and also the papers due to Anderson et al. And Michael Douglas et al. They have dealt with neural network approximations of the metric. And finally, there's another mode of attack for obtaining flat Calabi-Yau, Ricci flat Calabi-Yau metrics, namely Ricci Flow, and I'll talk about it if I have time. Now, the problem of approximating Ricci flat metrics by neural networks can be broken down into several different parts. The first and foremost is to realize that here, although this is going to be a machine learning exercise, there is no real data here. We are effectively solving some partial differential equation, and the only data that we possess or we can generate come from volumes over sampled points, or points sampled uniformly over a base Calabi-Yau geometry. One needs to define benchmarks for the flat metric, define various flatness measures, and the corresponding loss function for the machine learning endeavor. I'll also briefly mention what machine learning architecture we have used in this work, and therefore let me proceed. So the manner of generating points uniformly over a geometry that is Calabi-Yau is relatively non-trivial. So here, what we do, and this is a process that has been known a priori, here we consider a CC hypersurface which is embedded in some projective space. Keep the Quintic, the Fermat Quintic at the back of your mind as an example for this. Here, initially, the idea is to sample points uniformly with respect to a Fubini-Study metric that you inherit from the ambient space. So one samples points, or we sample points from a sphere randomly, and then we we choose pairs of points randomly, and we draw lines, and wherever these lines intersect the base geometry, we accept that as a valid point sampled uniformly with respect to the Fubini-Study metric on the Calabi-Yau. Now, this allows one to evaluate numerical integrations in a straightforward manner, and we always use the Fubini-Study metric as a measure for this sampling process. Here's an example of our sampling process on the complex torus, and here the complex torus can be viewed as 3 Riemann sheets glued together through branch cuts, and we identify and categorize patches here, and we also note the overlaps of patches because the metric has to transform meaningfully across different patches if it's to be a valid metric. Now, the kind of metrics so we are hunting for Ricci flat metrics, and how we benchmark our process is as follows. It has 3 different components. One is the Ricci flatness of the metric, one is scalaricity of the metric, and the final point being how the metric transforms between different patches, whether or not it transforms in a meaningful way. We define these quantities as follows. The sigma measure essentially should drop down to 0 in the limit one approaches a Ricci flat metric. The kappa measure, which imposes scalaricity on the metric, should also approach 0, and the mu measure, which considers the agreement or disagreement of the metric over different patches, should also in some limit reduce to 0. Now we combine all these losses linearly and construct this loss function written at the top of the slide. Now the architecture we use for this purpose is a neural network architecture, which is a bit modular. So we have two neural networks, and we construct the metric, or rather deconstruct the metric in terms of an LDL decomposition. And one of the networks supplies the eigenvalues for the metric, and the other network supplies the off-diagonal entries in the lower triangular matrix L that appears in the LDL decomposition of this positive definite object G. Now, some of the results are as follows. So for the Fermat Quintic, we sampled around 500,000 points using the sampling procedure I described earlier. And we let a neural network train over multiple epochs. And here we show how the sigma measure has changed as a function of, as the learning progresses. The plots at the bottom, they also, they essentially denote different, two different ways of computing volumes. And one can show that if they agree, the sigma measure is indeed approaching 0. The black distribution denotes the state of affairs before training began, and the blue dots represent these quantities following training. Now, the previous example was considering only the sigma measure as the loss. When we include the other two measures, the mu and the kappa measures for the loss, we see that the trends support the idea that neural networks can indeed approximate Calabi-Yau metrics or Ricci flat Calabi-Yau metrics in some limit of a well-trained neural network. Now, one of the other things that we found interesting was discrete symmetries. This is not directly relevant in the endeavor for obtaining Ricci flat Calabi-Yau metrics, but I will highlight how these come into the picture nonetheless. Now, discrete symmetries play a crucial role in constraining models in string theory, and they can help explain fundamental questions such as why is the proton stable? And the origin of discrete symmetries is poorly understood. In the language of superstring theory, these symmetries cannot simply be conjectured, rather discovered as isometries of the compactification space. So therefore, classifying discrete symmetries over Calabi-Yau geometries is a very useful endeavor if you're a string model builder. Now, the process of obtaining or classifying these discrete symmetries is non-trivial, and Volker Braun in 2011 or so classified a list of classified all freely acting symmetries over complete intersection Calabi-Yau geometries, and work with Philip Candelas and Andre Lucas in collaboration yielded a new process of computing symmetries of the quotients of Calabi-Yau geometries that you obtain from the freely acting symmetries. And here in this process, and I invite you to read this paper, I don't want to distract from the main topic here, but there's a lot of wonderful projective representation theory and geometric invariant theory involved here. And one is able to classify discrete symmetries of all CC quotients.
Challenger, you have 5 more minutes.
I have 5 more minutes. All right, thank you. Here's an example of some symmetry groups that appear in this classification. I've highlighted some in red because they are R-symmetries and they do not preserve when they act on the holomorphic 3 form, they give it a non-trivial phase. So classification of symmetries of data sets or of geometries, broadly speaking, is a problem that is common to both machine learners and mathematical physicists. So as an interesting exercise, we thought that as the Calabi-Yau metric is being approximated during the course of training, how can we also see discrete symmetries being learned in the process? This is a very inefficient way of obtaining discrete symmetries, but it might provide useful ideas moving forward. So here what we do is, during the same course of training of examples of which I was showing earlier, we define this quantity delta. Now, delta essentially computes the extent to which a symmetry has been realized in the neural network. Here, this symmetry, tau, acts on the homogeneous coordinates z, and if this quantity is 0, then you would declare the neural network to be invariant under this symmetry. And so we deliberately made use of certain symmetries, and certain symmetries were left out in the training process for obtaining the metric. And for one such symmetry that was left out, we computed this measure delta, and we see this extent of symmetry learning to be improving over the course of training, as shown by the blue curve. Whereas if we pick a random non-symmetry of the geometry, then we see that, that no learning effectively happens for that symmetry. How much time do I have?
You now have 2 more minutes, and then you're cutting into your question time.
All right, thanks. I shouldn't take longer than that. So I'll just briefly touch upon Ricci Flow. So here, the idea is this functional due to Perelman, which appears towards the bottom of the slide, is a functional that depends on the metric as well as this other function dilaton. And once you reduce this, once you minimize this functional, you get this differential equation, which is the flow equation that guides that the metric follows on this geometry. And there are theoretical guarantees that say that once you start with a metric, say for example the Fubini-Study metric, and you follow this differential equation, this flow equation, you should be able to arrive at the Ricci flat metric in that same Kähler class in this geometry. Now, this Fubini-Study metric is defined through a Kähler potential, and it leads to the metric which I've written at the bottom of this slide. And this is a valid starting point for Kähler-Ricci flow. Now, we tried this exercise on a real torus, which is depicted, which is endowed with this natural metric, whose curvature is denoted by varying shades of blue and red, essentially showing that the curvature at the top and the bottom of the donut is essentially 0, and the geometry is positively curved on the outside of the torus, and the inside of the torus has negative curvature. Now, if you consider some annular coordinate that forms a full circle and call it x2, then if you monitor the curvature of the metric following Ricci flow, you see this interesting behavior where, or predicted behavior rather, where you start by having this varying curvature denoted by the blue plot, blue line in the plot on the bottom right. And as you progress through the course of Ricci flow, you essentially reduce to a flat or an approximately flat metric, whose curvatures would then be given by the donut in green. For the complex torus, one can play the same game and obtain similar results. And finally, so this sort of ends my talk, and I wanted to highlight a couple of other things, namely that machine learning and string theory have successfully combined, and there are a lot of data sets to play with. I've organized some of these data sets, which some of you might find useful. The data sets and their sizes and when they were conceived are as follows. The complete intersection Calabi-Yau threefolds, the Kreuzes-Karker data set of Calabi-Yau threefolds, supersymmetric bundles over Calabi-Yau manifolds, discrete symmetries of these geometries, CC fourfolds, and so on. And new data sets are being painstakingly created, and machine learning string theorists have been working on these data sets and many other such data sets, with the first such papers appearing in 2017. There are many interesting research directions one can conceive through the influx of machine learning into the field. And a lot of this has been tackled by a number of mathematicians and machine learners and string theorists. Predicting topological properties of stringy geometries was one of the first examples that demonstrated that topological properties of stringy geometries can indeed be machine learned. This is work due to Yang-Hui He. Studying invariances of smooth Calabi-Yau threefolds, and there are possible hints that one can derive from work due to Taco Cohen, Rishi Kondor, and more recently by Sven Krippendorf and others. Understanding string-derived standard models, in particular the line bundle constructions over CCs, studying moduli spaces of these bundles, further developing machine learning strategies for obtaining Ricci flat Calabi-Yau metrics, and ultimately towards discovering the correct string vacuum, and as well as understanding swampland conjectures and so on. There are also other more mathematical applications that appear. So work due to Fabian Roulet show that machine learning can be effective in solving systems of nonlinear Diophantine equations. These are all helpful to a string model builder and also to pure mathematicians. Thank you.
All right, thank you very much, Challenger, for this very nice talk. Are there questions?
I have a simple question. That was a very nice talk. This is George Minich. So this is a wonderful work and approach, but a very simple physics question is essentially, what sets the energy scale? I mean, ultimately, you want to compute masses, right? So you want to get the dimensions. Do you put a Planck scale in by hand, or you envision something other non-trivial happening?
I suspect there would be very many non-trivial things happening, and I guess the first idea would be to actually get a handle on computing these metrics or approximating these metrics to as good an approximation as one possibly can. And after that, various other complications would arise, and there are members in the audience here who are much more knowledgeable about that than I am.
But even for the metric that if you wanted to compute and to your satisfaction, essentially you would just put in the scale in, right? You just basically say it's Planckian, that's it.
Well, here I'm going to say that there are no such scales involved here. I mean, here the corresponding optimization problem that you're solving, here if you are meeting certain criteria. So for example, the approach through Donaldson's algorithm essentially shows that if you increase the basis of the degree of the basis of invariant polynomials that you essentially use in the algorithm, then you slowly approach the flat metric. And so there the scale is dependent on the degree of the polynomials or the invariants that you are going to use. Here, a convergence analysis has not been done. It might have been done very recently, and I might not have seen it, but we suspect that there will be convergence guarantees here as well. And I
understand that if you want just to do it purely mathematically, but you have a physics question in the back of your head, right? You're basically trying to understand the mass spectrum. So this, I mean, obviously all the observed masses are nothing compared to the Planck scale, which is the only scale that you put in, right? Of course, string theory should not have any scales and only dimensional parameters, no dimensional. That's the dream, right? But I could imagine that you're just basically saying, look, my Calabi-Yau is Planckian, and essentially I put in that scale by hand. But maybe you're not worrying about this at the moment. You know,
yeah, at the moment we have completely ignored such considerations. So if one did have a workflow to compute the masses from some string theory model, then one can compare what values you get, you know, and compare it to the experimental values, and look at higher energy particles, say QCD, and others. But yes, we have not considered such things. It seems to be at a very early stage.
There is a comment here from Sven saying about you can, of course, once you get a moduli stabilization, you have a prediction. I agree. I agree. But I'm just wondering in this particular approach, right? I think the scale has to be put in by hand, and then you have to worry about moduli stabilization. Of course, this different scales could emerge. But I can only imagine couple scales, Planck, SUSY breaking scale, or gut scale, unless there's some amazing new non-perturbative effects, right, that you will uncover that are somehow generated. But anyway, okay, I think you answered my question. Thank you.
Well, thank you for the question.
No problem.
Are there further questions? Can I ask one?
Yeah.
Let me check to actually not go over time myself. So I have two questions. So depending on how much time we have or how long it takes to answer them, I will only ask one. So let me start by asking about the symmetries. Yeah. So in order to discover these, you don't need the Ricci flat metric or anything. You could really just take the Fubini-Study metric and check whether this is symmetric or not. I mean, whether sort of at z and tau times z, you get the same answer. So for this, you don't need any of what you discussed previously.
Yes, absolutely. You could. So the point was to highlight that we are getting discrete symmetries as a side benefit. It doesn't have anything to do necessarily with computing a metric. To be specific, you could be learning the identity function and still be discovering or seeing rather symmetries being learned. So here, this is not meant to be a procedure for computing or classifying symmetries over Calabi-Yau geometries or symmetries of metrics, etc., but rather meant to showcase that these symmetries are actually being learned, which is a non-trivial statement because it is not a priori clear why the training dynamics of the neural network should be such that these symmetries are being learned.
Well, if the answer is unique and it converges to the unique a metric, then of course it also has to satisfy the symmetry.
Sorry, say that again?
I mean, the Calabi-Yau metric is unique. So once you found this unique metric on the space that you put in on the symmetric point in complex structure moduli space, of course, this unique metric will respect the symmetry.
Yes.
The defense is a bit, I mean, it's expected. Of course, it's nice to see that it does, but it's not, I mean, it's not something that's an extra benefit of the neural network in some sense.
Oh, no, definitely. So the point was not to classify discrete symmetries using this manner because it just simply wouldn't work. We have to solve the inverse problem of what I showed to be able to classify symmetries. And the idea was to show that the training dynamics during the course of learning in neural networks is rather non-trivial, and it would be interesting to understand why this symmetry is being learned in the first place.
Okay, good. In the interest of time, we have to stop here. So thank you very much again, Challenger.